Lisa was there.
Started. Ma'am, started. Please continue.
Oh, it's okay. You need to wait for Tagisa. I think he has already.
Yeah, hopefully he will join in between. Maybe for some reason he is disconnected. But, he should join. Yeah. Maybe some network issue maybe on his side.
Yeah. So we can start now.
Probably we can start. Yeah, in the meantime, we can start.
So good afternoon, everyone. Today we have 15th lecture of weekly online lecture series on radar meteorology course, jointly organized by South Asian Meteorological Association and CUSAT. So today we have Dr. K. Amar Jyothi. She'll be discussing about quality control and processing of DWR data assimilation in NWP models. Before starting the session, first I invite Dr. Professor Someshwar Das sir for welcome address. Please, sir.
Okay, thank you very much, Dr. Srikala.
Thank you, sir.
Good afternoon, everybody. Professor AVM, Dr. Ajit Tyagi Saab, the President of SAMA. Today's distinguished speaker, Dr. K. Amar Jyothi, and also my old colleague at NCMRWF, and other members of the organizing committee, Dr. Millie Ghosh, Dr. Jayanti Pal, and for the first time, of course, today, Dr. Jayanti is participating in organizing the lecture. Of course, yes, she has been a member of the organizing committee, but silently supporting from the background. And today in the front side. Okay, and representative from Bangladesh, Mr. Sahalam, and our other colleagues, Dr. Rohini from SAPU. Good afternoon once again. Welcome on behalf of the South Asian Meteorological Association and ACARR, the Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology. Well, as you know, because this is the first time for Dr. Amar Jyothi as a speaker, therefore, I just like to brief about this lecture series to her. Basically, others, of course, already know it. This is a continuation of our efforts on capacity building of the people of South Asia and the member countries of the non-aligned movement. As I just said earlier that we had conducted the first online lecture series on atmospheric physics that was jointly organized by SAMA and the SRM Institute of Science and Technology at Chennai. Our second lecture series was on WRF modeling system, and that was organized jointly by SAMA and CDAC, the Center for Development of Advanced Computing at Pune. Our third lecture series was organized on satellite meteorology, and that was jointly organized by SAMA and the Birla Institute of Technology, MESRA. And this is our fourth lecture series on radar meteorology, and it is being jointly organized with ACARR and CUSAT. As most of you know, the syllabus of the lecture series has been designed based on the feedback and requirements of the member countries of SAMA. The lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of radar meteorology. This lecture series started in the month of May, sometimes 25th of May, and will continue till November. We have about more than 20 lectures scheduled in this lecture series. As I mentioned earlier, we have got registrations of about nearly 1,200 people from about 48 countries. And that means there are also the member countries from the non-aligned movement, because SAMA has only 9 member countries of South Asia, but because NAM and other institutional members are also there, so their member countries also become eligible to participate in the programs conducted by SAMA. So as a result, for this lecture series, we have got 48 participants from 48 countries from almost, you can say, different corners of the world. And therefore, many of them have different time zones, and therefore, they are not able to attend the lectures live, and so they attend it on the YouTube later on as per their convenience. because all the lectures are also recorded and archived on the YouTube. At the end of the lecture, we have the question and answer sessions. So all the participants are requested to write their questions in the question and answer box, and it will be answered by the speaker at the end. We have also announced earlier that at the end of the lecture series, we have got a online test we conducted, the midterm test already, after completing 50% of the lectures. And at the end of the lecture series, we shall have the final test, online test, in which, based upon the scores of the candidates, we shall also give them grade certificates like outstanding or excellent, very good, etc. But of course, all the participants will get a participation certificate. All the candidates which have more than 75% attendance of the live lectures, they will also get a special citation or special certificates for the attendance. And those, of course, who will score in the final test, above 85% and so on, they will get the grade certificates also. So please write down your questions in the question and answer box, and will be answered by Dr. Amar Jyothi. As she will be introduced, she is the expert on radar meteorology, has done a lot of work, especially on radar data processing, quality control, which is so important because otherwise general people only see the images taken by radar, but it's more important to process them and quality control them before we can use them in the NWP models or before we can assimilate it in the NWP models. Therefore, quality control of the radar data and radar data processing is a very important topic. And Dr. Amar Jyothi is expert in that. She has extensively worked in this, both in ISRO before joining NCMRWF, as well as she has got collaborations with the, I think, Australian University, etc. So anyway, she will be introduced in detail shortly after this. So thank you very much once again. Enjoy the lecture. And over from my side, Dr. Srikala.
Thank you, sir. Now I invite AVM retired Professor Aditya sir for presidential address.
Thank you, Srikala and Professor Someshwar Das, the speaker of the day, Dr. Amar Jyothi, organizing committee members, participants. Well, I extend heartiest welcome after celebrating Onam festival. We had a break of one Saturday. So again, we are in the series of the radar lectures. Over a period of time, we have built up right from the basics to the various products of the radar, and now we are going to have today's lecture on the data assimilation, which is a very important aspect of quality control and its use in the weather prediction tools, right from the nowcast, short range, and even beyond that. So it's a very important lecture, and I'm happy that Amar Jyothi is working on this. She is also working on the developing rainfall maps, daily rainfall maps using satellite radar and surface data. So the application of the radar is being seen in all the sectors being used, right from severe weather monitoring, cyclones, fault lines, to the prediction in the nowcast and the numerical weather prediction, and also mapping of the rainfall in the time and space variables. So that's a great use of the radar, and I'm sure these lectures are bringing out all these aspects very, very clearly. And as Dr. Somesh has brought out, yes, please participate, interactively ask questions, and also use the YouTube channel if you want to further go into details, and you are welcome to interact with our distinguished speakers to further upgrade your knowledge. As a mentor, they will be happy to guide you. So once again, welcome all of you. Thanks to Amar Jyothi for today's lecture. Over to you, Srikala.
Thank you, sir. Before starting the lecture, I invite Dr. Jayanti Pal to give a brief introduction about Dr. K. Amar Jyothi.
Thank you, ma'am. I'm really glad to introduce our today's speaker, Dr. K. Amar Jyothi, ma'am. She did her master degree in physics from Osmania University, Hyderabad, and holds a PhD from SB University. Dr. Amar Jyothi has worked as a research fellow at both Indian Space Research Organization and EASTRAC. Her research mainly focuses on rain microphysics, scattering simulation of raindrops, and the dynamic and microphysical evolution of convective storms. She has also contributed and worked towards the development of algorithms for polarimetric radar data products and relative calibrations. Currently, she is working as a scientist E at the National Center for Medium Range Weather Forecasting, NCMRWF, where her work is centered on the quality processing of Doppler weather radar data for numerical weather prediction applications. Among her significant contributions, some are the development of products such as mosaic of radar reflectivity and multi-source rainfall analysis. She is now engaged in the development of national-scale high-resolution rainfall product using radar and multi-satellite data. With that, I'd like to warmly welcome Dr. Amar Jyothi ma'am to the platform for her lecture. Thank you, ma'am.
Thank you all. So I'll be sharing my screen.
You can share. Yeah. It's fine.
Yeah. Thank you, everyone. Good afternoon to one and all. Myself, Amar Jyothi, and today I'm going to speak on quality control and processing of DWR data for assimilation and NWP models. The outline of my talk goes like this. So I'll be showing the network of the operational Doppler weather radars and how do we do monitoring, the pre-processing, the quality control, which is very much essential for the NWP applications. Starting with the National Network of Operational Doppler Weather Radars. We have around 37 operational Doppler weather radars in India, like operated by IMD. And the link that is provided is the link which will take us to the operational Doppler weather radars, which is a combination of ASC and expand Doppler weather radars. And yeah, and we can see that the foothills has got the more number of expanded Doppler weather radars, and the East Coast has got the S-band and C-band Doppler weather radars, and this count of the operational Doppler weather radars is going to increase more, and we are going to process huge amount of data in near future. So the applications of and the processing of the DWR data is also going to increase. The first and foremost is the is the monitoring of the Doppler weather radar observations. So as we have more number of observations coming from all the operational Doppler weather radars, it is very much essential to monitor the amount of data that we receive. And this is updated at every 12-hour cycle, every 6-hour cycle at our NCMRWF website. In the monitoring charts, we can see how much is the amount of data and what are the data that we are receiving. And these are the data that is passed for the assimilation process. One of the first and foremost thing whenever we receive the Doppler weather radar data is the quality. We need to have a preparedness of the system. This is the workflow of how the data is, after archiving of the data, how the data is processed, and for the till the final product. This is the entire operating system. I'll be like discussing, like first we will be selecting the data, and the data is matched. We have various data files coming, so the data matching is very important. The continuity is of the data is checked. The first and foremost is the quality control. radar data has got a lot of quality issues. So something like clutter, ring check, electromagnetic interferences, anomalous propagation issues. After all this quality aspects are checked, and then we match it for the same time, all the radar data, that is what the time matching does. Then we generate the quality flags for each bin or the grid in which the data has been processed for various perspectives. One is like the reflectivity data, which is processed for the three-dimensional processing for the assimilation, and the other is the reflectivity, which goes for the mosaic product. The radial winds, which is processed for de-aliasing, and then it is thinned or super-robed for, and then coordinate transfer, and finally the assimilation. The reflectivity product is again converted, and the gridded product goes for either the generation of the rainfall product or the latent heat nudging process. So this is the rough operational radar pre-processing system at NCMRWF. The first is the quality control. We know that the radar data has got its advantage, like it has got very high spatial and temporal resolution data. But in addition to that, along with that, it comes with a lot of errors, biases, irrelevant data, especially ground clutters, surface clutters like mountains, bridges, ships in the reflectivity. And not only that, this data actually at the signal processing level, it is removed by using some clutter filters. But even after applying this clutter filters at the signal processing level, this data creep into our the raw data set. And to remove completely this noisy data at the signal processing level, it will have its difficulty. It can suppress the rainfall or the important information while doing too much of signal processing. So some of the things are left over, and that data needs to be quality controlled. I will show you during my lecture like how the data will look with bad quality, and why the data needs to be quality controlled and all. So the first and foremost is the radial velocity. The radar data, the tendency of the radar data, we get the radial velocity, and it's very much essential to have a good quality radial velocity. And the radial velocity will have its own errors, and some of the thing which needs to be quality controlled in case of radial velocities, like ground clutter. We need to remove the ground clutter. We need to look at the standard deviation of the radial velocity. We need to, whatever the aliasing is there, the de-aliasing need to be done for the radial velocity. Non-meteorological echoes needs to be considered. The scan strategy in which the radar is operating is also need to be considered, and signal to noise ratio. So all these aspects come for the quality control in terms of the radial velocity. This is the typical example for the first and foremost is the standard deviation of radial velocity. And here, this is the typical example from the paper I have taken. This is from the 2011 paper. Here we can see that this is a classic example. One is of the bird migration, and this is a reflectivity corresponding to that, and this is the radial velocity corresponding to that by bird migration. This is a second example where it is the rain echo, and this is the radial velocity correspond to that. And this is a standard deviation which is considered on the y-axis, and the x-axis is the reflectivity. Very clearly, the bird echo and the rain echo, when we the radial velocity, when we do a standard deviation, it shows a significant difference in the standard deviation of radial velocity for a bird echo, and this is the standard deviation of radial velocity for a rain echo. So such kind of significant differences, when it is there, it is very easily you can remove those bird echoes, and you can consider only the radial velocity which corresponds to the rain echo. Bird echoes or the insects, or it could be some other kind of biological scatters which we get, can also be assimilated, but it needs to be processed in a different way, unlike a rain echo. So this is the standard deviation of radial velocity. So here I have mentioned that three different types. One is the locust swarms, and the other one is the bird flocks, and the third is the ground clutter. It is a constant like a building or any other constant clutters. And what we see is that the standard deviation of radial velocity, the expected for a locust swarms, will be in the range of 1 to 3 meter per second. For bird flocks, it's high 3 to 6 meter per second, which we have seen right now. And ground clutter, it is 0 to 0.1 meter per second. This is such kind of, we can see overlap here also, where bird flocks or locust swarms, in some cases it can overlap, but the standard deviation of radial velocity will give us one of the factor to remove the noisy data. If you see the locust swarm, it will have moderate variability because it more or less it flows along with the wind flow, the locust swarms, and the bird flocks. This has also got high variability, as for the previous slide we have seen the example, and it is very erratic. And if we come to the ground clutter, so definitely ground clutter will exhibit the radial velocity near zero. And when we take the standard deviation of the radial velocity, it will be around 0 to 0.1 meter per second. This is another thing that we frequently see is like the aliasing of the radial velocity. And the Nyquist velocity is the one of the key factor through which we judge whether the radial velocity is aliased or not. So de-aliasing of the radial velocity is very important. And there are numerous methods which are involved for the de-aliasing of the radial velocity. And some of the methods which I have listed are here: the phase unwrapping method, the WAD method, 4DD method, region-based de-aliasing method, 3D de-aliasing, dual radar de-aliasing. So when we say it's like the quality control, it can be done using one of the method. Why so many methods? There are so many aspects. One is that when we look into the operational scenario, we need to look into the computational aspect and the availability of the other sources. And when we do it at a research purpose, yes, we can do so many comparisons with respect to the so many methods. But the situation in which the radar data is scanned, like what is your target? If your target is only with respect to the rain echoes and not a deep convective echo, if it is a stratiform type of an echo, or what will happen when there is a lot of turbulence and convective style of echo, and for cyclone case. So each and every case is different, and an algorithm which is applicable may not work in the same fashion for all the cases. So we have so many algorithms, and when we do research, it's very important to test for our case, for that scenario, what will work. So I'll go with the first method, that is the phase unwrapping algorithm. So this is the algorithm where it will check the gradient check, where it will check how the phase is, whether the phase is continuous or not with respect to the radially. If there is a drastic change in the gradient of the radial velocity, then it will, with respect to the Nyquist velocity, then it will check it. Otherwise, it will take that. So such kind of phase unwrapping method, which checks for the continuity of the velocity fields, has got its advantages and disadvantages. So it is applied for the isolated convective cells or stratiform type of rain, where you don't find the velocity gradients to be too steep. If the velocity gradient is too steep, this kind of algorithm fails, and you will not get the satisfied result. And the reference for this, you can see the Goldstein et al. In the year 1988. These are very old but very robust kind of algorithms. The other very famous algorithm is the WAD-based method. And this is the example which I have taken. So this WAD-based algorithm, before processing, what it does is like it removes, suppose you have an isolated echoes corresponding to a convective system and all, or any, it could be any clutter or anything. all the isolated echoes will be removed, and the continuous data only will be processed for this VAT-based method. The VAT-based method has got the advantages, like it checks for all the azimuth, like across the azimuths and all. And the VAT method, by default, it assumes that the wind flow is across the radially, if you see, or across, it's like wind is homogeneously flowing. So with that assumption, this VAT algorithm is applied. If you don't have a homogeneous system, then this algorithm will fail. And this is the VAT-based algorithms reference, that is Quinn et al. In the year 2011. This is a very good method and very robust method. Another very robust method is the 4DD de-aliasing method, which uses both the spatial and temporal continuity. The term itself says it's 4DD, the three-dimensional of the volume of the space plus the time. It goes back and it checks the continuity of the system, and definitely it needs the entire volume scan as well as the previous scans record in order to process this. So definitely it will lead to computational complexity. Such kind of algorithm is good, but it has got its own drawback, because this also depends on VAT profile. So if your VAD, which has got any issue in that continuous azimuthal the 360, it assumes the sinusoidal check. If that has got some issue, then you will have issue in your VAD profile. Then definitely it will have its dependency on the 4DD, and the velocity de-aliasing will have some issue. So this is the James et al. 2001 reference paper for this 4DD de-aliasing method. Another very popular method is the region-based de-aliasing, which assumes the texture of the Doppler radial velocity, and it searches in that spatially. And this region-based method is easy in the sense computationally it is less. It searches in a very, it takes a grid and then searches how the spatial texture is, and it applies the spatial coherence, it checks. So this method, because it is easy, it is, and the computational load is less, this method is applied for the operational scenario, but with few more checks. And these another very recent and the popular method by Valentin Loaf is the 3D unravel method. So I personally like this method because it not only considers the radial velocity in bins wise, it considers the radial velocity azimuthally and as well as the elevation wise. While considering the three-dimensional data, it will see how is that the vertical structure of a storm and all, and it gives very beautifully. It can be the de-aliasing is removed. So this is this method is very valuable for the severe weather analysis and for the storm tracking, and where the wind changes, pattern changes are rapidly happening. So for convective storms, and even if you have mountainous regions, because the lowest elevations will have issues when you have the radar at mountainous regions, and the radial velocity will have some issue. The 3D unravel method works very pretty well in those cases. Another method is the dual radar. So maybe with more network of operational Doppler weather radars, we can try for this dual radar based de-aliasing. So this is again, this seems to be a very robust method, because whenever you have a radar scan, and if that radar scan has got some issue, and you don't have a radial velocity, then you can compensate with the another Doppler weather radar. So but then we need to keep in mind that both the radars should have some no, it should not be so far that it is both of them are looking at the extreme end of system. So both should have very good not so close, not so far. It should be able to see the system, and then the de-aliasing will be done. And this is also another robust way with involved with computational complexity. This is the example of algorithm of velocity de-aliasing, which is applied for the Delhi radar. where we can see that there are a lot of the radial velocity has got a lot of spikes, and you have got the system also. The system itself is embedded in the noise. And the region based method, if you don't remove this noise kind of thing and then apply the region based method, it will consider the entire thing as the event itself, and then it will do the de-aliasing, and which will lead to such kind of chaotic structure of the radial winds. Definitely when we have such kind of chaotic structure, and this structure will cause problem for our assimilation. And this is the 3D method. During the same period, I have applied the 3D method, and this has worked very well. It could because it considers the three-dimensional structure. It has very carefully seen that wherever the clutter or the noises are present, it has removed. It could tackle the noises, and it could give us the radial de-aliased winds. So we can see that the negative and the positive, so the continuity is also there. So though it will and if you can see that this last example where the noises are less, the region based performs well. So what we are supposed to do is, like, we need to remove all the noise data, and then we can apply this region based or the 3D. 3D we generally we do it for the research purpose, and the region based we do it for the operational perspective. Now after the radial velocity is looked for the sign change, standard deviation, and de-aliasing, so the radial velocity is ready for the assimilation. Now the next is the reflectivity. So reflectivity is used for various applications. We see reflectivity alone itself to see how is the movement of a storm or a rain echo or a hail echo or any other echo. And the other, if we have anomalous propagation or spikes and all, how the radial velocity data will be either removed, or we set a quality flags, so that these quality flags, when they say that these qualities are bad, so they will not be considered for further assimilation. This is the Delhi typical IMD strategy 1 and strategy 2, and this is the clutter map. We can see that for the first few kilometers, the presence of clutter, and more than here I've plotted more than 90% of the probability of the clutter in one particular zone. In order to develop this clutter map, I have taken the pre-monsoon season, the prior to the rain echo season, where the sky is clear, and I have considered for nearly around 3 months of cases where I will consider that I will be more sure, because more than 90%, when I say that there is a constant target at that place, then those places clutter. This I have taken from the total reflectivity field, because in the reflectivity field, there is a issue that the clutter filter removes this kind of noise. So the total reflectivity will have this clutter map. So this clutter map will give an idea of the presence of the constant clutter. So this has got its own applications. Why we have generated this clutter map? Because generally whenever we see a map, we say that clutter is a noisy remove. So but then here we have done a relative calibration adjustment. See, the general ideal strategy is, like, if you see that we have a ground clutter, and we have due to super refraction, we have this all this kind of echoes and this noise due to insects, clutters, and all. This is ideally the signal what we have, and this is after the correction. All this noisy data generally we consider not relevant, especially in case of rain echo. Definitely it is not relevant, but there is a way in which this data is segregated. One we have used it for the calibration purpose before removing, and after removing we use it for the applications. Either it may go for the assimilation, or it may go for the product generation. So this is the typical clutter removal procedure for a single polarized radar. So most of our radars are single polarized, but now the X-band, the foothills radars, whatever recent radars we have got, they all are polarimetric Doppler weather radars. So we have got now the polarimetric game also coming in with more variables and more option to remove the noise and the attenuation and other factors to look into, which we will be seeing in the coming slides. So this is a typical flow chart of how the ground clutter echo is considered and how we apply the threshold and the texture variations we see, and then Gabela filter is applied, and then all the isolated echoes and which are non-meteorological echoes are removed. And this is another reflectivity algorithm, that is the Steiner algorithm. This is a very old algorithm, but I like because this algorithm will not completely remove the data, because when I say that whenever we are applying, we should be very sure that the loss of signal is to partially to some extent is fine, but we should not lose any isolated echoes, which is very obvious in case of pre-monsoon season. We will be, and the main advantage of radar is got it can identify those isolated convective echoes. So whenever we apply this Steiner algorithm, takes care, it also considers the entire 3D volume scan of data and processes the 3D volume scan of data and retains the convective and echoes. So what the all the non core echoes and all, it will consider with a reflectivity threshold, and it will classify this as the non-core echoes and the core echoes. So based on the reflectivity threshold and also with the 3D structure. So this is a typical example of in the year 2019, where Delhi NCR has experienced severe hailstorm. So this kind of the sole core echoes I was saying, when you have a convective system, you may have very small regions of convective core, though it is part of the bigger system, but the development and evolution, if you see, it is a very small convective core system, and the movement of this in the radar reflectivity. And we have, because the Delhi Doppler weather radar is a C-band polarimetric Doppler weather radar, and we have got the radio sonde launches, and also using the temperature profile and as well as the Doppler weather radar data, we have computed the severe hail index. You can see that a few of the places we have uh, the severe hail index has crossed the 80% probability, and the maximum expected hail size has also got more around it is more or less, it is in the range of 1, but we have a higher probability of the maximum expected hail size. And the probability of severe hail also, you can see that it has got very severe probability. So this was a very severe case of a hailstorm. So after removing the noise and all, when we see the signal, it looks pretty good. And another is the biological clutter. I have already shown you the case study of the birds and as well as the rain echo through the standard deviation of velocity. But this is the, here I'm going to talk, when we have polarimetric observations, we need to take advantage of the polarimetric observations too. And here we consider, because we have the threshold criteria, how much is the standard deviation for what we can apply for the biological scatters, like a locust swarms or insects or birds or a rain echo. Accordingly, we can apply the threshold, and whether we should mask those data or we should remove or not remove. Another criteria what we can consider, because there is overlap of the thresholds that we when we apply, so that can be considered by using the polarimetric observations, where we can take the differential reflectivity and as well as correlation coefficient. These two, differential reflectivity and correlation coefficient, they are very good indicators for the biological clutter, because the correlation coefficient, generally it has got very good correlation, especially for the rain and hail case. Hail it is partially, and rain more. Rain has got more than 93 or 95.95 is the criteria what we can give it for the correlation coefficient for rain. But whereas if we have birds, it will have very poor correlation coefficient. Along with that, differential reflectivity, you can see that it has got very high correlation for the insects. So if we combine reflectivity, Doppler velocity, differential reflectivity, and correlation coefficient together, we can classify the various types of categories of noises or the unwanted signal in the radar. So like it could be a flying debris, chaff, bats, insects, birds, and whether to apply mask or not apply mask. We have the fuzzy based algorithm which can be applied once we have the polarimetric observations. And we had a typical locust swarm case study over the Delhi and Lucknow region. So this is on 2020. Here we can see that very strong signal we were getting, but initially we thought this is a rain echo, and we were very carefully dealing this not to remove the noise signal, because we just want to classify what is noise and what is locust swarm and what is rain echo. This example, we can see that we have got the locust, the moment of the locust swarm, we have the noise, and we have the rain echo. So it was challenging for us to prove that this is the locust swarm echo which Delhi and the Uttar Pradesh region has experienced. And this is how the radar reflectivity, what we have observed during that time. We have seen that the maximum radar reflectivity has reached up to 68 dBz. And then we have seen the radial velocity, we have seen the standard deviation of the radial velocity, and then we have seen the 3D view of the radar reflectivity. Here we can see that the locust, in order to differentiate between a locust swarm and a deep convective cloud, we can see that this locust swarm echo was not able to go beyond 1 kilometer height. Whenever we have a deep convective system, so the deep convective system will also exhibit very large reflectivity. But corresponding to that, if we see that vertical extent of a deep convective clouds, it will reach up to a height of around 10, 12, or more than that also we have seen. But here, this a strong echo, what we were seeing along with the clutter and along with the rain signal, only the rain signal was able to go beyond 3-4 kilometers. But this locust swarm echo was restricted within the 1 kilometer. And based on all the criteria which I have mentioned, we have segregated the rain echo and the swarm echo. So it was a very interesting study to identify a locust swarm in case of a Delhi radar. And when we have a dual polarized, as I said, like when we have dual polarized radar, so the clutter removal will be a bit easy, because when we find such kind of locust swarms, when here the correlation coefficient will show a poor correlation coefficient rather than the reflectivity, trust alone the reflectivity and consider it as a signal. So here I'll be listing out some of the criteria. One is the correlation coefficient, and the meteorological echoes will have typically around 0.95. So that's a very good indicator, we can say. And the clutter echoes like ground, returns, buildings, trees will exhibit very poor correlation coefficient. And differential reflectivity for the buildings, and also that exhibits how much is the drop size, the distribution and all, we can clearly see with respect to the ZDR, the differential reflectivity very beautifully. It will show how is that ZDR for rain, ZDR for hail, or any other hydrometeor. But for the buildings and all, it is close to 0. Here there is one tricky thing. When we have seen the differential reflectivity for hailstorm case, what we saw was the differential reflectivity was showing around 0, or I can say 0 to 1. So we were surprised to see high reflectivity. That's also a criteria of ground clutter. But differential reflectivity alone, if you consider, it has shown us very poor differential reflectivity near to 0. This is because of the tumbling of the hailstone effect in case of S-band radar. But again, the scenario changes for C-band and X-band case. But that is one of the typical thing what we have seen when we have considered the differential reflectivity. Another is the specific differential phase. This is another polarimetric parameter which is also exhibit close to 0. And it also depends on the type of the objects what we can consider, what we have considered. So overall, when we have dual polarized radar, so the clutter removal using a combination of correlation coefficient, differential reflectivity, and specific differential phase will be a very good clutter removal. Another very important aspect when we deal with a lot of we have a lot of X-band Doppler weather radars coming up, and at the foothills, and because C-band and X-band Doppler weather radars have this attenuation playing a crucial role, unlike S-band radar where the attenuation will be around 0.06 dB per kilometer for 100 mm per hour. That is what it is written in the Raghavan book, and we can compute and see. For the S-band radar, it is typically it is okay. We don't have to worry that much about the attenuation. So the causes of attenuation, it could be rain, hail, and what frequency of radar are you working with, and what type of hydrometeors, whether it's like it could be a cloud water, it could be ice, or it could be the atmospheric gases. The atmospheric gases, anyhow, we don't have to worry, because prior to that, the atmospheric gas correction will be taken care, and then only we need to do only with respect to the hydrometeor based attenuation correction. So the single polarized based attenuation correction, when we see, so this is a typical formula. So when we know that the reflectivity and rainfall are related, and this is how the typical C-band radar empirical relationship between the attenuation and the rainfall, and or the reflectivity, we can see that how the AZ relationship. And once you have your attenuation, then the two-way attenuation is computed, and this two-way attenuation is corrected, is added to your raw radar reflectivity, and finally you have the corrected radar reflectivity. So all this attenuation correction algorithms I have taken from Bringi and Chandrasekhar, the textbook. So another is the dual, when we have the advantage of dual polarized radar, so the attenuation correction, we have linear depolarization ratio, which is another polarimetric parameter, and it plays a very crucial role in the attenuation correction, because it is being a phase parameter, it is immune to the attenuation of the due to the rain. So by considering those advantages, and we take the linear linear phase parameter, linear phi dp, and then we correct the differential reflectivity, and this is the typical equation for the correction of the reflectivity, where the propagation phase is linear, the propagation phase is added to the differential reflectivity. This propagation phase itself is a little bit noisy, so we go for specific differential phase. The specific differential phase is computed using the FDP, and the specific differential phase is again, after computation, it is added to the differential our radar reflectivity, and we get the corrected reflectivity. And for S-band and C-band and X-band radar, so this is how they typically the coefficients are computed, and using the scattering simulations, we get this coefficients over a specific region. And this is a relationship between the specific attenuation and the KDP. We have and using this also we can compute the attenuation factor, and this attenuation factor can be added to the reflectivity, and we can correct the reflectivity when we have polarimetric system. And this empirical constant, this is again an empirical relationship. So this C1 constant is depends on the wavelength, the drop size distribution, and the rainfall properties. So usually we consider the scattering simulations. So because we get the drop size distribution using that, so we compute using the scattering simulations, and we have seen that this parameter C1 not only depends on the wavelength, the drop size distribution, and rainfall parameters, we have seen that it has also got dependency on the temperature. So by considering all these factors, we can derive the AH and KDP relationship. And another famous, the Z5 algorithm. So once we know that there is AH, the attenuation factor, and another is like ADP. This is the specific differential attenuation based on the differential reflectivity. The AH is computed for the reflectivity, and this ADP is computed for the differential reflectivity. Once we have the ADP computed, together AH and ADP play a crucial role in the correction of reflectivity and as well as the differential reflectivity. And this we have an iterative process, iterative, and accordingly iteratively we keep on applying the corrections for the reflectivity and as well as for the differential reflectivity. So this is the typical equations of the reflectivity correction and the differential reflectivity correction with respect to specific attenuation and the specific differential attenuation. So until we reach the convergence, this Z5 method, it continuously applies the correction. Another factor like what we consider apart from the attenuation is the beam broadening. So this is typically how the beam broadens with respect to the range. And this is the typical example of the Delhi where the orography is considered and how much the beam is shielded due to this. So accordingly, we can give threshold, or either we can, for the assimilation purpose, we don't consider this region. If you consider, then you need to consider only for the higher elevation. You need to be a little bit cautious when applying the beam shielding or any other correction algorithm. Either you correct it. If you have corrected, then accordingly you raise a quality flag to leave it to the assimilation person whether they can consider this or not. I will be telling you why more in the coming slides. And this is the radar reflectivity. This is for the Mohanbari region. There is an S-band radar, and we can see that though it is an S-band radar which can cover a region of 500 kilometers, but due to the orography of that region, we have very small region of rainfall, and this entire thing we have shielded, so we don't consider that region's reflectivity. We don't for the computation. Though we can consider from the higher elevations, but we be cautious up to what is the height of the echo that is reaching at that region. So the combining flags, as I said, the quality has got the various aspects. We have seen whether it is a ground clutter, biological clutter, or the birds, or any of the factors like attenuation. It could be beam shielding, or together we need to give a weighted rule of all that quality flags, and we have given the quality flags in the range of 0 to 1. There are two different ways to deal with that. A particular bin can experience the quality factors due to multiple factors. When one specific bin has multiple factors quality, we cannot either reject it or we can not accept it. So in order to do that, we have a weighted rule of quality flags giving in, and those weighted rule of quality flags goes to the assimilation people, and then we generate the quality flags like this, like 0, where it has, the data is whether it is valid, it has got very high quality without any, may have corrections, may not have corrections, but can be considered as a true data, and it can go for the assimilation. The other one is the suspicious data. because as I said, after removing of the noise also, we sometimes find a locust swarm echo which we have never expected to come in a radar signal. So such kind of quality flags, we raise it, and we say it's suspicious. So it is up to the when they assimilate whether to consider that data or not. And then the invalid data, where we are sure more than 90% that this data is from a constant clutter or building which needs to be removed. So these are the typical way of giving the quality flags in the ratio in the range of 0 to 1, and together combined we give a quality flag 0 to 1, combining with the attenuation, beam shielding, beam broadening, and all the aspects, and the combined effect we give, and then again we segregate that into the quality flags, whether it is valid or whether it is suspicious or whether it is the data needs to be rejected. uh, Once the data has got the quality flags, there is the calibration or the bias correction. The radar data is ready, but the radar data, after doing the calibrations, the native calibration, whether it is balloon based or any other, still the data, radar data will have some issues in the reflectivity. So such kind of thing can be addressed using different ways, and one of the way is using onboard real-time radar. So this is based on the GPM radar, so which is matched with a ground-based Delhi radar, so the precipitation radar. But of course, such kind of calibration has got certain limitations, and it cannot be done on a continuous scale, either due to the passes, or if at all there is a pass also, uh, at least there should be 5,000, or there is a count. It should be a stratiform type of a rain where the movement of the rain echo should not be very fast. So it should not be convective, it should be some stratiform type of rain. Such kind of rain echoes are matched by the volume matching method, and then the bias correction has been applied, and we see how much is the bias, and that bias factor, if we see this factor continuously, then for that particular radar we can say that this is the bias that is continuously persisting in this radar, and which needs to be added or accordingly corrected. As I said in earlier slide also, we had a clutter map. So we have taken the clutter map. So we always say clutter, come on, remove, remove, remove. Instead of removing the clutter data, now we have used this clutter data as a valid data to see how is the radar. So what we have seen is, like, this is the cumulative distribution for the clutter, and what we see is that generally this is one is the baseline and one is the actual real time clutter. If at all, only you need to see the clutter data points. If at all the clutter data points consistently show you that the clutter region, or if at all they show you that there is some deviation from the clutter, then you can say that the radar data, while maybe due to the maintenance or any other issue, if there is some issue in the system, it will show you a deviation, and that deviation can be addressed by this RCA kind of method. And this is one of the typical example of the Jaipur radar, where we have in the month of January and all, the radar has undergone for maintenance, and after maintenance we have seen that there is a typical shift in the calibration values, RCA values. So this could be a remote way of checking the health status of a radar without being present at that site after the maintenance work. So this is a very beautiful product which we have developed along with the Bureau of Meteorology, and where it will tell you how much is the deviation, and the radar data again needs to be, the radar needs to be cross checked, and so this is how you can give a feedback to the people who are working at that place with the radar. Once your data is processed and quality controlled, quality flags are raised, next the data is ready for your assimilation. So the assimilation, I will not go in detail about the assimilation. I'll be just saying that till superobing, the data is either you need to thin the data by doing some methods like superrobing, you cannot directly ingest the data. The data needs to be again processed. So again, this is left to the assimilation people, like what kind of, the how many azimuths they will take, how they will process this data, how much is the azimuths or radially they will consider for the superrobing and all. This is all based on the research experiments when we do, how many number of samples we can consider for the superrobe, because direct ingestion will have its issue. Here in this typical example, you can see if we ingest after superrobing also, not all the data can be passed. Again, the models will have its own checks with the background and all, and most I can say that we try to see that the minimal amount of data is rejected and the maximum amount of data is considered for the process of assimilation. And of course, there are certain advantages and as well as disadvantages, because by doing this, you have the reduction of the data. So computationally, it should be able to, in order to meet the computational demands, and you can have more efficient way of data assimilation, and it will improve the representativeness. And the challenges, like when because of the radar scan, you have temporal gaps, you have spatial gaps, and when you go for the higher altitudes, because especially when you have at the mountainous regions, the coverage is another aspect, the blocking due to mountains is another aspect, and the loss of small scale information. So definitely there will be potential for bias, and the choice of your binning or the number of samples is another thing. So once the data goes for the assimilation, the other perspective is the we take all the data to generate a mosaic of radar reflectivity. When you have a system passing on and when you have a network of radars, so the mosaic is one of the best way to see how is the system it is passing. So you can once everything is done, then you can look for the how much is the data overlap it is there, which radar data you can consider, which you cannot consider. So all that, this is a typical example of mosaic of radar reflectivity. This product is now getting upgraded because we have more number of radars, and so we are thinking, because now this product is at every 15 minutes, so we will see every 10 minutes how the how many number of radars we can accommodate to, and the we can clearly show the migration of the systems in a, especially on a, if you have a squall line, it will be very beautifully shown. So finally, I would like to conclude that the quality is a very, very important thing. And whenever we deal with Doppler weather radar data, we need to look into the quality factors before using it in any of the applications, whether it is for the rainfall or whether it is for the reflectivity studies with for the convective studies, or whether it is for the assimilation, radial velocity assimilation. It is very much essential to look for the quality and pre-process the Doppler weather radar data. Thank you, and I'm ready to take up questions.
Thank you, Dr. Amar Jyothi. It is a very informative talk. I think it will be useful to those who try to assimilate NWP products, means DWR products in NWP models. So thank you for your talk. Actually, we have a photo session now. So I request all of you to switch on the camera.
Vijay, yes, sir, it's done.
Okay. So now we have a question answer session. It should be moderated by Dr. Mili Ghosh.
Thank you, ma'am. There are a few questions. Actually, This topic was very much important and a little bit difficult also. Questions are less, I think. See, first question is, which method is better for noise removal in received reflectivity signal?
So I'm not going to discuss about the signal processing perspective. I'm going to discuss only which method I've already shown you. The Steiner algorithm is very good to remove the noise, and so that's what noise is, a very generalized term. What kind of a noise you want to remove, and the Steiner will definitely do its job. It's a very good algorithm.
Thank you, ma'am. The next question is, do you get LAN interference and discuss filtering, please?
Yes, yeah, electromagnetic interference. I think when I was working with Mumbai Radar, we had this electromagnetic interference as a very big issue with the naval base and all. So we had written so many algorithms in order to remove those electromagnetic interference. Yes, we do get it, and but I think all those things are taken care at the radar site itself. But if we continuously find this electromagnetic interference, then we have to report it, because while removing that data, you remove your important signal also due to this interference. It has to be dealt at the radar site itself. So the entire data, that region needs to be masked or need to be taken care. Right now we deal only with that.
Thank you, ma'am. The next question is, which among the many factors do give the most significant error? Can we reduce it by increasing or adjusting positioning of the radars?
Like, which is the parameter? You mean to say the radar parameter? Ma'am, can you read the question once again?
Which among the many factors do give the most significant error?
Okay.
I think it is in two parts. Question is in two parts. First part is, which among the many factors do give the most significant error?
Okay.
And the second part is, can we reduce it by increasing or adjusting positioning of the radars?
See, the radar, the installation or the positioning, whenever I say, it's like, it's a very big procedure when a radar is installed. It is actually a site check needs to be done. So after that, after so many checks only, and how much is the data we are getting, and the need of the radar in that particular region, and the mapping, everything is done, and positioning of the shifting the position, unless if it is an X-band mobile radar, you cannot simply shift the radar position.
Okay, thank you, ma'am. The next is, what are the advantages of noise mapping? And what about other sources of interference? How to
Noise
map them?
mapping, I already I've said it is a clutter. So when you have a constant clutter a building, and when you know that this particular azimuth, this particular range, when you have it as a building, it should show all the time. After the radar maintenance, sometimes what we find is like there is a shift in that the position of that. So that means there is some azimuthal shift. Generally everything is taken care, but sometimes it may be a loosening of a screw. So it could be anything which can give you the mismatch in the relative calibration adjustment, and which is a remote way of, in a very good way to see, and how much is the shift in that. Ideally, if the shift persisting, then that calibration parameter need to be added. That, along with that satellite based volume matching method which I was telling, it will be an ideal way of to bias correct your reflectivity parameter.
Thank you, ma'am. One participant wants to see the table, slide number 25. You have shown some table, ma'am. That slide he wants to see again.
Yeah, this is for the biological clutter.
Ma'am, please share, na? Yeah.
Oh, it's not shared, so. Yeah.
Yeah, but he has not put any question related to this, but only tabular view he wants to see.
Okay. So this is with respect to the birds, insects, bats, flying debris, shaft, anything. Like how is that reflectivity? And we have polarimetric. So how the differential reflectivity and correlation coefficient behaves. So
Okay,
definitely for the noise signals and all, the correlation coefficient will be very low. This is one of the key indicator where we can remove the biological clutter, which may not be true in case of single polarized radar.
Thank you, ma'am.
Yeah.
Now there is no question in this question answer chat box, and there is no question in YouTube also. So I think over to Dr. Srikala. Thank you, ma'am.
Thank you, ma'am.
Thank
Now I invite Dr. Johini L. Bawar to extend vote of thanks.
Can you stop sharing the slides, Dr. Amar Jyothi?
Yeah.
Thank you, Dr. Srikala. So, esteemed guests, distinguished speakers, and respected colleagues, as we conclude the 15th lecture of the Radar Meteorology lecture series, it is my honor to extend the vote of thanks on behalf of South Asian Meteorological Association SAMA, the Advanced Center for Atmospheric Radar Research ACARR, and the Cochin University of Science and Technology CUSAT, India. Firstly, I express our gratitude to Professor Someshwar Das, Secretary of SAMA, for his welcome address and the overview of lecture series that set the precedent for the lecture. We extend our heartfelt gratitude to AVM retired Professor Dr. Ajit Tyagi sir, President of SAMA, for his educational opening remarks and unwavering dedication to guiding the youth of our generation. We would like to express our sincere commendation and gratitude to our eminent speaker, Dr. K. Amar Jyothi, Scientist E, NCMRWF India, for your enlightening lecture on the quality control and processing of the DWR data, which needs to be used for assimilation in NWP models. We deeply appreciate Dr. Jayanti Lal for the articulate introduction conveyed by her for our guest speaker today. We also deeply appreciate Dr. Mili Ghosh Nilala, BIT Mestra, Ranchi, India, for her efforts on moderating the question and answer session and making it a lively and productive discussion. A big shout out and our heartfelt gratitude to Dr. Srikala, Assistant Professor at CUSAT, for overseeing the entire session of today. Lastly, I would like to thank all the participants for the active engagement and contributions. And once again, thank you all present today and those working on the sidelines also for making this session a success. Thank you, Srikala.
Thank you, Rohini. Now, Professor Someshwar Das ji, please give some concluding remarks.
Okay. Thank you, Dr. Srikala. I think today's talk was definitely very, very important, but a little bit probably difficult for most of the participants or many participants, as they may be unfamiliar to this topic of radar data processing. Most people, I understand, they just are interested in looking at the image of radar reflectivity or radial velocity or other products, but hardly many of them, they try to go into deeper side and then try to process or utilize the radar data for many purposes, especially for the numerical weather prediction, or for any matter, for that matter, the processing and quality control of the data is very important. Because unless you have a good quality data, you cannot use it in the assimilation in the model, nor you can use for any other purpose, like rainfall or retrieval of the cloud microphysical parameters, because your data itself will be faulty. So this is a very important topic which Dr. Amar Jyothi has nicely summarized all the techniques used for quality control and processing of the radar data. Yeah, I mean, many of you know that any instrument or every instrument has its own instrumental error, first of all, right? And so also radar is an instrument. and therefore radar will have a instrumental error, which generally is provided by the manufacturer of the radar. But beside the instrumental error, of course, there are many other things like already explained by Dr. Amar Jyothi. Like you can have unwanted noise or clutter because of the presence of a building, which is anyway constant, and day to day, if it is seen, then it can be easily filtered out. Or the presence of the trees, or the blocking by the mountains, which will be a constant thing, permanent thing, so it can be easily filtered out. But the noise because of the flying of the birds and locusts or any flying object for that matter, like aircrafts or any other thing, they are like a temporary transient features, right? And so sometimes it becomes difficult to understand whether it is a signal for a weather system or it is just a noise because of the flying birds. So those things have to be filtered out very carefully. And Dr. Amar Jyothi has already described many methods for that. These quality control data, you may be knowing that in NWP, all the observations which are received, whether it is temperature from a thermometer or humidity from a hygrometer or anything, or wind from the anemometer, everything, all the data are first of all quality control and processed before it enters into the data assimilation system. And so also is the case for the radar. Right? We cannot straight away use the raw data of the radar into the model. And so Dr. Amar Jyothi's work is a very, very important interface before it is injected into the model. Data is injected in the model. And as you know, your next two lectures are going to be on the assimilation of Doppler radar data in the NWP models. First of all, by Dr. Anand Kumar Das from IMD, who assimilates the Doppler weather radar data in the WRF model. And afterwards, the next lecture would be on the assimilation of radar data in the NCM regional model, that is National Center for Medium Range Weather Forecasting Unified Model, the regional version of that. So Dr. Rautray will be speaking on that. So the next two lectures are very, very important, before which this lecture was a crucial link to process the quality control data. And so I hope that at least those of you who are not familiar have got an exposure of what it is. And you can go through the lectures many times, as many times as you want on the YouTube, because it is already available in the YouTube. If you wanted to see any slide repeatedly, you can just go to the slide and just click, hold, or pause, and then keep watching the slide to understand more deeply. So all the lectures are available on the YouTube, and please go through that, and please know for sure that this is a very, very important topic. Before you can use the radar data in any model or for any other application. Okay, so I hope all of you have enjoyed, and thank you so much once again, Dr. Amar Jyothi, for nicely summarizing all the difficult procedures for radar data quality control procedure and processing. Thank you once again. Tagi Saab will not be available. He should be a message. So probably after this, we can conclude, right?
Thank you, sir, for your concluding remarks. So I think we can conclude the session. And thank you, Amar Jyothi.
Thank you all for organizing this. Thank you so much.
Thank you.